Hi. So initially for my design, I had an idea that I would have a ribbon-like shape that would twist as the tamper seal when the bottle cap was turned to the left. And after a certain amount of stress was put on the ribbon, it would snap. But I had a difficulty when I was replicating that in CAD. So I had a different idea where I would basically have a band with mechanical bridge or a notch that would snap upon an excess in stress. So the initial performance for the 140 millimeter diameter uh, basically had the band not snapping, and we had the let me see the constraints for the material were set as let me find it real quick. So I had the Young's modulus set at 2,758 megapascals and the Poisson's ratio as 0.35. And I had the material be, I named it as a brittle plastic, and it was supposed to be elastic. Um, so I chose this material basically to restrict elastic compliance, and so that I also limited the global structural displacement to a less than 0.15 millimeters under load. So during the baseline evaluation, I simulated a standard consumer removal force of 50 pounds force, which is also 222 newtons for the load. I think I actually also set it at 250 just as an excess here to see if that would be enough to snap the band, but that was unfortunately not. So typically, um, right from the model right now, I would most definitely have to increase the notch size. So as you can see here, uh, the gap is here, and it's I think it's around 0.08 centimeters in diameter. So this would definitely have to increase in size. And so the global stress distributed across the tamper ribbon peaked at just 18.18 megapascals. So from the looks of it, the best solution is to increase the size of the notch I created at the side of the plastic seal. And let me show you the von Mises. So this is what it looks like after the test. And so the primary objective for the mechanism was to have an irreversible physical fracture during the initial opening sequence to provide a proof of breach because our selected material has a definitive ultimate tensile strength of 48 megapascals, the recorded peak stress of 18.18 megapascals. Uh, as you can see, let me pull out the Mises. So here you can see the red stress is at 18.18. The majority of the stress is induced in this notch at the very face of the notch. So the max is, as you can see, 18.18 megapascals. And so this results in a structural factor of safety of 2.6. And instead of snapping cleanly, the bridges have an behave as an elastic structural part, which flexes without breaking. And it's basically highlighted that the standard ductile polymers would undergo local necking, microyielding, and stretching under these conditions. And ductile stretching is a failure mode for security seals, as it allows easier to cheat the cap past the bottle threads without physically cracking the indicator band. So this, as you can see here, only bent the band itself instead of actually snapping it. And this is just clearly not enough force for the band to actually have a semblance of a snapping indicator. Um, I would, lastly, to improve upon the design, I initially had the idea to just increase the radius of the notch and have it cover a larger area on the band so that it would not require as much stress for the band to snap. So let me pull that out really quickly. So for the new notch here, initially it had a smaller diameter, as you can see, and currently it has a 0.32 diameter. So try this. Yep. Sorry, a radius of 0.32 inches. So let me delete this. And hopefully, I've yet to test whether or not this works. I just don't have the time currently, and future testing should result in a better performance for the notch. But at this moment, uh, I'm not sure if that's the case. So just overall, just to improve upon the design, I would just have to increase the radius and also see if decreasing the radius of the actual band itself would also improve the ability for it to snap. And that's pretty much all.